Hey everyone, today I'm going to show you how to extract the max Courant number using Python in HEC RAS. Why does this matter? Well, it helps us find where and when the Courant number limit gets exceeded in our model. The Courant number is a key QAQC parameter, and for a good, stable model, it should stay under the limit. So let's dive in. HEC RAS actually has guidelines for the Courant number. For shallow water equations, the max allowed is 3, but ideally, it should be around 1 or less. For diffusion wave approximation, experience says max 5, but it's best to keep it close to 2. So we always want to keep the Courant number under these recommended limits. Now, in HEC RAS, there are different kinds of Courant numbers. Let me explain them. First, there's the phase Courant from the HDF file. Next, the continuous phase Courant from RAS mapper, which isn't a single discrete value. Then, the Courant number map based on velocity and length from RAS mapper. Fourth, the Courant based on residence time from RAS mapper. And lastly, there's the cell Courant from HDF or RAS mapper. You can easily open these HDF files with the HDF viewer. Talking more about the phase Courant number in the HDF, it's calculated using normal phase velocity, time step, and distance between cells across the face. This phase Courant is the only one you can manually calculate and compare accurately with the HDF results. I am going to talk about how this phase Courant is used by HEC RAS to come up with different variations. HEC RAS uses interpolation to get the phase point Courant from the phase Courant from HDF and finally calculates the continuous phase Courant on RAS mapper. The max phase Courant from HDF calculated across all cell faces is used by the rendering engine to compute Courant map on RAS mapper. Cell Courant is velocity at cell center times time step divided by cell length. The velocity info for cell Courant comes from post-processing. So yeah, there's quite a bit to keep track of. Now, I'll show you how to open the HDF file. Here's the plan file, P.03, HDF. Let's go to that location and open it with the HDF viewer. Once you open it, go to Results, then HDF Output, Output Blocks, Base Output, HDF Time Series, and finally 2D Flow Areas. Inside Perimeter 1, your 2D area, go to Computations. Here you'll find computed velocity and water surface results. These are the parameters calculated during the model run. But we don't have the phase Courant number yet. To get that, we need to tell the model to write it into the HDF file. How? Go to the HDF parameters, scroll down until you find the phase Courant option, and turn it on. I'm also turning on an additional related option, then hit OK. Save the plan. Now, we have to run the plan again. If it's open, close it first, then recompute. Let's see how long the run takes. Alright, let's wait until the simulation finishes. Okay, now the model has fully run, so we can go check the results in the HDF file. To do that, let's go to the model folder where the plan P.03 is saved. Look for the P.03 HDF file and open it with the HDF viewer. Once you open it, navigate to Results, then Unsteady, Output, Output Blocks, Base Output, Unsteady Time Series, 2D Flow Areas, and then into the study area called Perimeter 1. Here you'll see the phase Courant number available. Let's open that. Okay, so now you can see the Courant number is computed. Let's explore what's inside. You'll see different values listed here. Along the x-axis, these are basically the cell faces and time steps along y-axis. Scrolling to the right, you'll notice the really high numbers on top represent the cell face numbers. As you look down along y-axis, numbers 1 through 48 indicate the different time steps. Each time step is based on the mapping output interval set in HEC RAS when you run the plan. So, this mapping output interval controls the intervals shown here. For example, at cell face 89,219 and time step 40, the phase Courant number is 0.06. We can find this location and exact data, time of occurrence in RAS mapper by checking the exact cell face and time step. Let's go to the geometry here and open the Find tool. We want to make sure we're searching by face, not cell, so enter 89,219 to find the exact face number. This is the face we're investigating in the HDF file. If you want to know the exact time for that time step, plot the any time series, say velocity and go to time step 40. This corresponds to the date September 1, 2008, at 9:45 am, and shows us exactly where and when this Courant number is happening. So this way you can find the exact location of Courant number violations in RAS mapper and modify your cell mesh if necessary. Okay, alright, I want to circle back to the different versions of the Courant number one more time and break down how each is calculated. First up, the phase Courant number as it appears in the HDF file. It's based on the normal phase velocity, the time step, and the distance between adjacent cell centers across that specific face. This phase Courant number is the only parameter that can be manually calculated and accurately compared with the computed value in HEC RAS. So, if you want an exact value for your QAQC checks, the face Courant is the way to go, even though there's currently a bug that shows it as half of the true value, so just double it for accuracy. All the other Courant numbers are based on this face Courant from the HDF file. For example, HEC RAS uses interpolation to calculate the phase point Courant number, which is then sent to the rendering engine to form the continuous phase Courant number in RAS mapper. Let me show what the continuous phase Courant number means in RAS mapper. Go to the results section, and then in additional 2D options, plot the phase Courant number. That's what I mean when I say continuous Courant number. It's the smooth result you see in RAS mapper, built off the interpolated phase Courant values. There's also the current number based on velocity divided by length in RAS mapper. Here, the max phase Courant value for a cell is calculated and set as a single constant value per cell in RAS mapper. When you add the results map layer, go to hydraulics, and plot velocity divided by length, it gives you a constant value for each cell, based on the maximum phase Courant number. Just keep in mind it's not the exact computed value but an interpolated or rendered value coming from that process. The other one is the cell Courant number. This one uses the formula, velocity at the cell center times the time step, divided by the characteristic cell length. The velocity at cell center comes from post-processing and is interpolated, so it's also not the exact value. If you turn on the option in HEC RAS to write out cell Courant numbers, you'll see it in the HDF file, calculated from this formula. To sum up, the face Courant number from HEC RAS is the most accurate and precise current number to use for QAQC. If you need something reliable for checking if the Courant number was ever exceeded, use that. Just remember to double it because of the bug right now, but I think HEC is going to fix this in the next version of RAS. Now, let's jump into the main part. Let's open up this face Courant number in the HDF. Say, you want to extract all the Courant values greater than 1 across your model. It's almost impossible to do by hand since there are thousands of cell faces. This is where Python scripting comes in. You can use Python to automatically pull the locations and times where the face Courant number goes above 1 based on the mapping output intervals in HEC RAS. I've got a script ready that can do this. If you want it, comment below and I'll share the script. For this demo, I just copy-pasted the HDF path, set up the script, and ran it. After running, the script writes a QAQC report in PDF, listing every face Courant violation. I also set it to check for any cell water surface area errors above 0.01 foot. The results show every Courant number greater than 1 for perimeter 1, that's your 2D area name, so you get a clear idea where issues pop up. You can use RAS mapper to check the specific phase and time step, see what's going on, and adjust things like adding break lines or resizing cells if needed. For this example, the values are all close to 1, so it's not a big concern. But if you see lots of high Courant numbers, this report will be a huge help. That's all for now. If you need the script or have questions, drop a comment below. I'd be happy to help out. Thanks, and see you next time.